I wanted to explain you briefly about multi-arm bandits. I'll spend about 15-20 minutes, give you the intuition, lots of references. I'll try to simplify the concept because, as I told you, we can spend a whole 30 hours just on multi-arm-bandits. But I want to give you the intuition. Imagine if you have these nine ads, or nine, not necessarily ads, these could be just nine thumbnails that we want to experiment with. Now, how do we do it smartly? So there is this very nice, again, the same problem is used by Google also. So imagine if I want to show an ad on Google, I could have different creatives or different ads that I have available. Suppose you want to show some ad on YouTube. Let's say you're creating a YouTube ad and you're working in marketing of a company, right? You have 3 ads that you've done. Now you want to now say, hey, which ad works better? But you don't have enough money, or you don't want to just burn money showing ads to tons of people to collect data. You want to spend minimum money to find which ad works best. And lot of advertising by Google. Again, I understand about online advertising because I worked in that for a very long time at Yahoo Labs and also Amazon. So in ads, picking the right ad is a huge problem. Remember, a huge chunk of Google's revenue comes just from ads. So similarly, Netflix wants to pick the right one. How do you do it? The objective here is, can you pick the best one with minimal resources or minimal amount of traffic, or minimum amount of traffic dedicated to all these treatments? Okay. So for this, there is, again, I'll point you to this blog, very nice blog. This whole concept of multi-arm-bandits starts as follows. Okay. So let me give you the intuition of the problem and the setup so that we'll see how it gets connected to what we're studying. So imagine if you have this machine. This is called as this is typically your slot machine. It's called as a slot machine, right? So you have, let's say, you went to a casino. You have, let's say, some 10 slot machines. 1, 2, 3. Okay, let me use a different color. So let's assume this is slot machine 1, 2, 3, 4, 5, 6, 7, etc. Bunch of slot machines. You put some money. You pull the lever on the slot machine, and it either gives you money or it says, sorry, no money, put money back again. This is like typical gambling stuff, right? Now your objective is, imagine if you have some 10 such slot machines. Every slot machine works differently. Now your goal is to say, using minimum money, or at least minimal amount of money. Just a second, please. So using minimal amount of money, can you figure out which of these is the most beneficial for you? This is the setup of multi-arm-bandits. Again, remember, this is very similar to our YouTube ads, or this is very similar to our Netflix thumbnails, because I want to show this to a smallest number of customers. But by showing it to the smallest number of customers, or by trying it out and showing it to smallest number of customers, I want to find out which of these 9 works the best. Okay, so multi-arm-bandits is a fairly complex topic, but let me give you the simple intuition behind it. Okay, so the way we can do it is as follows. Let's take our standard A/B test. Let's take a standard A/B test. In A/B test, what do? We have our control, we have our treatment. Control is also called as A, treatment is also called as B. Okay, let's assume we allocate some 90% traffic here, 1% traffic here. Let's assume we fix these percentages and we run the experiment for a few days. And let's assume treatment works better. So we run the experiment for a few days. Okay. So in this case, what are we doing? We are exploring. The keyword that's used here is, we are exploring whether control is better or treatment is better. Okay. This should be 10%. I'm sorry. Right. We are exploring now. But once we realize that the treatment is working better, right, we don't use the control anymore. We give 100% of the traffic to the treatment, or whatever ad or whatever visual we are showing. So initially we were exploring by giving only 10% of traffic to the treatment initially. And when we realize that the treatment is working well, we exploit now. So these are called as explore-exploit strategies. First we explored by giving a small percentage of traffic. But once we have statistically rigorous results with good confidence intervals that yes, the ad that I'm showing in the treatment or the thumbnail that I'm showing in the treatment is working great, we start exploiting. We say, hey, Let's not worry about the control. Let's show everybody the treatment. So in this case, we are exploring and then we are completely exploiting. We are no more exploring here, right? So in A/B test, till the time I start on another control, so this treatment now becomes the default control. Again, I'll compare it with something else and so on and so forth, so on and so forth, right? So in the case of multi-arm bandits, there are basically three broad strategies. I'll give you the intuition of all of them. There is something called as epsilon greedy strategy. What does the epsilon greedy strategy say? It says, okay, so let's take a concrete example, right? So suppose if I have thumbnail 1, I have thumbnail 2. Just let's take a simple example, thumbnail 3 and thumbnail 4. Netflix example, right? So I will set up some epsilon. Okay, so with epsilon, I'll say, hey folks, my epsilon is, let's say, okay, let me pick a reasonable, let's say my epsilon is 10%. Okay, which means 1 minus epsilon is 90%. This is what is called as epsilon greedy strategy. Very simple strategy in multi-arm bandits. Works reasonably well in practice. Not the most optimal strategy, but works reasonably well. The idea here is as follows. First, I'll send some customers here. I'll send some customers here. I'll send some customers. Small number of customers, not too many. Let's assume I send some 100 customers here, 100 customers here, 100 customers here, 100 customers here. And what is our metric that we're measuring? Our metric is, let's say, click-through rate, which means how many people clicked on this thumbnail. So let's assume of the 100 people, let's assume 2% people clicked on it. Let's assume here 4% people clicked on it. Here, let's assume 1% people clicked on it. And here, let's assume some 3% people clicked on it. So I send only a small amount of traffic here. But now, this is getting the highest clicks. As soon as I have some reasonable data of click-through rate, again, I can also estimate this click-through rate. Don't forget that. I can estimate, again, this is my click-through rate, right? I can get a confidence interval around click-through rate, again, using bootstrapping samples. I can do bootstrap samples again and get confidence intervals around these, right? I can do that technically. Okay, let's not divert ourselves into that direction because I want to focus specifically on the epsilon greedy strategy. So the epsilon greedy strategy says, just a second, just to be sure. I'm a little confused about epsilon and 1 minus epsilon. What term is used where? Because, sorry, just a second. Is epsilon greedy? Just a second. I just want to make sure that I'm not making a mistake. And this is useless article. Okay. 1 second. So is epsilon 10% or 90% is what I'm a little confused with. Just to be sure, I don't want to make that mistake. Q learning. Again, all these concepts were initially designed in reinforcement learning. This is explore, exploit. Okay, epsilon strategy with epsilon explore. Got it. Okay, so my terminology is right. Okay, I just had that slight doubt. Okay, so in epsilon greedy strategy, your epsilon is typically like a reasonably small percentage, right? So this epsilon is for explore. Okay, I always get confused whether epsilon is explore or 1 minus epsilon is explore. This is your exploit probability. So what do we do here? Again, what is exploring and exploiting? Exploiting basically means that you pick the best guy and you make the most out of it. Exploring means you're continuously seeing whether control is better or treatment is better in the A/B test setup. Exploiting basically means once you know that somebody is good, you will send everything to that person. But the modern multi-arm bandits say, let's not do that. Their argument here is this. So I've sent a bunch of people, I got some percentages. Now this is the winner, right? This is the best guy right now. This is the best guy at this point of time. So let's say initially at time 0, we don't know anything. So we sent all the people. At time T1, right? This thumbnail is the best. So what will I do? I will exploit this, which means because my 1 minus epsilon is 90%, 90% of the times I will keep showing this thumbnail. 10% of the times I am still exploring. I'm not fully exploiting. I will explore and I'll say 10% of the times I will pick one of these 3 people randomly. Right? So 90% of the times I have this. So which means roughly 3.33% of the times I will still show this thumbnail one. 3.33% of time I will still have this. 3.33% of time I'll have this. Because why are we doing this? Why are we wasting resources on this? Because it could so happen that after a while, because we just started running this test right now, right? After a while, it could so happen that this 3% guy on whom we are still sending some traffic, this 3%, this T4, this thumbnail 4, even though we are sending 90% traffic, probably because of the pattern of the traffic or the 100 random users that were assigned here, this guy's percentage could still say 4% click-through rate, which means 4% of users clicked on it. This guy's might increase to 6%. Suppose at time T2, at every time interval, we see who is the winner. And if we are confident about it, using the confidence intervals and bootstrap samples, right, then we can simply say, hey, this guy is the winner, so give 90% here. So the key idea of epsilon greedy strategy is, unlike A/B tests where you're exploring and then you're exploiting completely, unlike that, we are saying at all times, I want to continuously explore. And 90% of the times I'm exploiting, but 10% of the times I want to continue exploring so that I might find a hidden gem, right? So that's very, very important. Now, here comes, so this is what is epsilon greedy. So there is a question here, which is how do we deal with anonymous logins to ensure they don't have noise in the data? So it's completely possible that some experiments could be run just on only logged in users. I think I mentioned this in the morning, right? There are some experiments which will run only on a small subset of users. I've seen experiments which are run just only on Prime customers for Amazon, right? So experimental designer, whoever is trying to design the experiment, can say, hey, all these non-logged in users can mess up things. So I don't want to even show these experiments to non-logged in users. I'll only show it to logged in users. It's a business decision that has to be taken care of. That's all is epsilon greedy. Very simple strategy, not the best strategy, but a good strategy. Then there is this concept called as Thompson sampling, which is a Bayesian approach. I'll give you the intuition behind it and the ideas on how they work. Okay. So now again, let's go back to our original problem here, right? So we have, let's say T1, T2, 4 thumbnails, right? So we have T3, T4. This is slightly more involved mathematically, but I'll give you the high-level intuition so that you understand it. Okay, so this is Thompson sampling, which is Bayesian in nature. Okay, let's take the same click-through rate example because it's easier to understand, right? So the idea here is as follows. Okay, so we send some 100 customers here, send some 100 customers here, we send some 100 customers here, some 100 customers here. Now, our metric is click-through rate, right? If you think about it, your click-throughs, right, whether somebody clicks or not, is a binomial random variable. Okay, because somebody can either click or not click. This is very much like heads or tails, right? But we don't know if for heads or tails, we know that there is a 50% probability that it's heads, 50% probability that it's tails. But for this ad, while the click event itself, whether somebody clicks on it or not, is a binomial random variable, we don't know what is the rate of that binomial random variable, right? If you have any binomial, suppose x is a binomial random variable, right? Suppose you have a random variable x, which is binomial, right? For heads and tails, the probability of getting heads is 0.5 and the probability of getting tails is 0.5. But you could have another binomial random variable. Again, all clicks are typically because you either have a click or a non-click. There are only 2 possibilities. So it's a binomial because there are 2 values, or it's a binary random variable. So we don't know what is this P. P is basically the probability of click, right? We still don't know what is the probability of click. We have to discover this probability of click. This is unknown, right? One thing that we can do now is we can say, hey, very nice. Of these 100 people, let's assume 3% of them clicked, 2% of them clicked, let's assume 4% of them clicked, 1% of them clicked. Now, can you say, hey, let's take one example, right? Let's take this guy. Can you say for T3 or thumbnail 3, this is a binomial random variable with the probability of success as 4%. No, you can't. Why can't you say that? Because this 4% value that you got is only from 100 people. There might be much larger number of people. If instead of 100, if I make it 10,000, this 4% can change. Look at this. From 100 people, 4% basically means 4 people clicked. If one less person clicked on it, it would have become 3%. That's the problem here, right? So we don't want to spend too much here. But the question that we have here is, we know that this value, let's call this random variable x3. We know that x3 is binomial random variable with some rate, but we don't know what that rate is. Here comes a very fun concept in statistics and probability theory called as posterior. So there is this whole concept in, again, without using too complex a terminology, we can use something called as Bayesian statistics, where we can say that this random variable, again, look at this p-value, right? Not the p-value in that way. This probability of click, this p is probability of click, right? This p is probability of click. We can say that this p itself has an underlying distribution. This p itself has an underlying distribution. That distribution is called as a beta distribution. Okay. So again, I know this could be slightly tricky if you're new to whole statistics. Suppose imagine I have a random variable x, right, with some mu and sigma. This mu itself could have another distribution. Again, from morning we're discussing this, right? We have taken the median difference. We have taken medians, right? We said these medians themselves can be random variables, which means they can have some distributions. Similarly, if you have a binomial random variable with some rate, this is typically called as the rate variable or the probability of success. This variable itself can have another distribution, and those distributions are called as beta distributions. Again, unless you have studied graduate level statistics, you may have never encountered this. So the idea of Thompson sampling says that yes, it uses this whole concept, right? So this is called the conjugate prior, by the way, in case you know that statistics part. So the idea here is, it says, hey, I have 4%, but I don't know exactly what this p value is. But I can represent this p using a distribution. This p I know, even with 100 values, I can come up with a reasonable distribution of this p, which is typically like a beta distribution, which looks like this. And over time, look at this, over time, what will happen is, I will try to find what is this p. Again, what is being happening here, unlike your simple epsilon greedy strategy, where you're simply taking the CTR and picking the winner. Here you're saying, no, I just don't want to do that. And Thompson sampling has a lot of statistical guarantees and a lot of rigorous proof that it works better than simple epsilon greedy. What it suggests is, hey, for this guy, for whom we see 4% click-through rate, using the data, I will try to estimate what is the distribution of this probability of success. And using conjugate priors, I know that it is a beta distribution. Now I try to estimate the parameters of this beta distribution. Now, at any point, just like, again, this whole thing is called Bayesian statistics because we use Bayes' theorem to estimate the parameters of the beta distribution. But the idea, again, is more or less the same. The idea of Thompson sampling is, while I have these 4 values, using a bunch of statistical gimmickry, of course, completely solid, scientifically backed and rigorous mathematics, I will still try to give more and more traffic. I will forward more and more traffic to that thumbnail where I think the probability of having, where I know that there is a higher probability of having, where I know that there is a higher probability of seeing a higher success rate. Again, epsilon greedy is more explicit in that. Epsilon greedy clearly says 10% of the times I am going to explore, 90% I am going to exploit. It clearly says that. On the other hand, the Thompson sampling based Bayesian system says I am not going to explicitly do that. I'm going to use some statistical concepts like conjugate priors and Bayesian statistics to constantly estimate which of them is the best, and I will give more proportion of traffic to those which I think has a higher probability of higher click-through rate. But it will keep sending it to everybody, right? So This is, oh yes, you're right. Somebody asked this question. Yes. So this whole beta distribution is done using conjugate priors, and you do a maximum a posteriori estimation. Yes, that's the underlying details. But since there are a lot of students who may not be comfortable with some of that math, I'm skipping that. But the idea here is as follows. I'm just giving you the intuition behind it. The idea is using a bunch of Bayesian statistics, we are still trying to find which of these has the highest probability of click rate. And we will give more and more traffic to those which have the highest probability of having the most click-through rate. Now, there is a third aspect to it, which is again more tricky than these two, which is called contextual bandits. Contextual bandits is basically saying, hey, imagine if I have T1, T2, T3, and T4. Right? Imagine if I have these 4 thumbnails that I can show. Suppose I get a customer. Suppose this customer comes from, let's say, let's pick a country. Let's assume he comes from Canada. Okay. And I know some details about this customer. I know that this customer has this age. I have some context around the customer, gender, age, other channels, other genres that he has watched. So the contextual bandit says, hey, for this customer, I already have a context. I know something about the customer. Now, amongst these 4, instead of not using this context, because I already know some context about this customer, I will try to predict what is the probability of click, right? Again, specifically for this type of customer, I'll try to predict the probability of click for this customer's context. Customer's context, you can get it through something called as a feature vector in machine learning. We'll say which country he belongs, what is the age. Based on all of that, I will try to find what is the click-through rate for each of these 4 thumbnails for this type of customer. And that is typically done using a bunch of machine learning algorithms. Contextual bandits is used quite extensively, but it is a slightly advanced topic for this discussion. Probably in one of the future live sessions, once you know good amount of machine learning, we can dive into contextual bandits, within which there are many subtypes. But the idea of contextual bandits is once I have to choose which of these thumbnails I have to show, I'm better off saying I have the context about this user. I will use this context along with all the information that I have about these 4 thumbnails and then combine that information to pick the best one for this guy. Contextual bandits is also used in recommendation systems at some of these companies. Okay, cool. So all in all, now you might say, hey, all this sounds a little superfluous. Why bother about all of this? There are a couple of reasons. One is, even if you use something very simple like epsilon greedy, it's a very simple strategy, right? It's basically epsilon exploration and 1 minus epsilon exploitation. Even a simple strategy like this, you can show both mathematically and through simulations that epsilon greedy is better than simple A/B tests. And there is rigorous mathematical proof and also real world impact that Thompson sampling based Bayesian statistics can work as well as, actually many times better than even epsilon greedy. Contextual bandits is literally the state of the art because we are not only using the context of the customer, we typically use machine learning models plus the whole concept of explore exploit strategies in this case, right? So without going too deep into that, I hope you have understood epsilon greedy clearly, if not others. These two are slightly more complex. We might have to cover them at a later